So again, we're applying here the formula for the volume of an object when we revolve something around the x-axis with the area between two curves. So we're not making a solid object, if you think about it. We're actually making something that has a hole on the inside, and you can kind of see it here to the right. You know, we have this shape here that we're looking at. Looks kind of like a leaf shape. But then as we revolve that around the x-axis, it's going to make this almost kind of an object that almost looks like a bowl on the outside, but on the inside it kind of looks like a funnel. And you can kind of visualize that a little bit there. I know it's hard to visualize something three-dimensional with a two-dimensional picture, but that's the idea. So let's take a look at what we would actually be doing here. Okay, using the formula that we looked at last Thursday. Okay, we could do this, if we think about it, kind of the same way we derived the idea of finding the area between two curves, except now we're talking about two different volumes. All right, so if we thought about this first of all as a solid bowl, just looking at the outside, that's made by that function y equals square root of x. Okay, now we also need to figure out what our boundaries are for this, because it says the region between these two. We aren't told specific values, so you would have to actually set, to find the bounds, you would have to set x squared equal to the square root of x. And this one you could figure out algebraically, or you could figure out logically. Okay, of course keep in mind the domain. If you figured this out algebraically, you would square both sides and then get everything on one side equal to 0, and then you could factor. You have x times x cubed minus 1, and if you continue to factor this with the difference of cubes, you get x minus 1 times x squared plus x plus 1. That does not have any real roots, but the x minus 1 and the x do. So x equals 0 and 1 are the two boundaries. Okay? So if I'm doing the volume of this whole thing as though it were a solid bowl, I would do the integral of pi times the function squared integrated from 1 to 2, sorry, not from 1 to 2, from 0 to 1. Okay? So that would be the entire thing. Then I would need to think of, okay, well, now I need to cut out the part of the bowl that I want to be empty. Okay? And that's this area right here. Just like we did area between two curves, we subtracted the lower one from the upper one. Here you can think of it as though we're subtracting the inside volume that we're cutting out from the whole solid. All right? It's almost like if you're eating a cantaloupe or something and you scoop out the inside, you know, or an avocado or whatever you like to eat. Okay? So this is the part we're scooping out. All right? So to do that, then we're going to subtract the volume that would contain revolved around the x-axis. So again, we have pi. We're going to have the same bounds from 0 to 1. And now that's the function x squared. So we're going to have x squared squared dx. Okay? Now, before we actually... well, let's go ahead and find these integrals, and then we'll make the connection and develop our formula. Okay. So you'll notice I have pi times the integral from 0 to 1 of square root of x squared. So that's just x dx So that's going to be pi times x squared over 2 evaluated from 0 to 1. Okay? So that's the first part. Minus pi times the integral from 0 to 1 of x squared squared, so x to the 4th dx. So that's pi times x to the 5th over 5 evaluated from 0 to 1. Okay? So now we evaluate our two integrals with the fundamental theorem of calculus. So I have 1/2 minus 0 minus pi times 1/5 minus 0. So I have a 1/2 pi minus 1/5 pi, and that's going to give us 1/5 is 2/10, so 5/10 minus 2/10, that's going to be 3/10 pi. And of course, since this is volume, it would be units cubed. You do not have to put units unless it's some type of a word problem. Okay? So that's the volume that that bowl would take up. That's not the volume inside this bowl. The volume inside this bowl would just be the 1/5 pi. Okay? That would be how much the bowl would contain. Okay? This, however, would tell us how much material you could say it would take to make this bowl. Alright?
Where are you getting your U cubed?
Just units cubed. Whatever our units of measure are, it would be cubic units. Okay.
What is the number there? Is that U triple?
U cubed.
Oh,
Just for units.
Yeah.
Whatever units cubed.
Why is it square root of x squared minus x squared? Like, why not reverse?
Why not reverse? That's a good question. If you remember what we were looking at when we did area between two curves, you always did the top curve minus the bottom curve. Alright? So here, the square root of x is this top part. The x squared is the bottom. So you do top minus bottom. Okay? Now, yeah. Go ahead.
Yeah, the last one. Why is it squared?
It's squared because if you remember our volume of any function revolved around the x-axis was pi times the function squared. Because what we're doing, if you remember, it all went back to the volume of a cylinder was pi r squared h. Okay? So in this case, r is our function. H, the height, that's taking the integral from a to b. Okay? That's how you take care of the height. Okay. Now, let's look a little bit more closely at what we did here. Okay? So, and let's generalize this a little bit for a formula. Okay? If I look at this, I did pi times the integral from a to b of the top squared, or we could say upper, the upper function squared, minus pi times the integral from a to b of the lower function squared. Okay? Now, if you think about some basic algebra and also our rules for integrals, okay, one thing that I can do is I can factor out the pi, okay, because they're both multiplied by pi. But then also remember, when we're subtracting integrals, you can actually put them together and subtract what's inside first, then take the integral, as opposed to taking two separate integrals and then subtracting them. So actually what I can do here is take the integral from a to b of the upper squared minus the lower squared. Okay? And that actually takes us to our formula, which is on our next slide here. Okay? If we have a region where the upper function is f of x and the lower function is g of x, and they intersect at a and b, or we could even just cut it off wherever we wanted between a and b, okay, and we revolve that around the x-axis, then its volume of revolution is given by pi times the integral from a to b of f of x squared minus g of x squared dx. Okay? So it's the upper squared minus the lower squared that you're taking the integral of. Okay? Okay. So thinking about our formula here, let's try this example. Okay? We're going to make kind of a ring shape here. If you were to look at this, all of these are going to be symmetrical circularly, but you know, this is going to look something like this, a ring, but it's going to be, it's going to kind of curve there, but it's going to be flat on the inside. Okay? So it's going to be flat. You might even have a ring at home that kind of looks this shape. You know, it's totally flat on the inside, but the outside is curved. Kind of might look like a wedding band or something like that. Okay? So, using our formula, first of all, we need to find the bounds here. Now, we didn't necessarily have to go from intersection point to intersection point, but commonly that's what we're doing here. So, how would we find A and B?
Y equals 3, so we can plug to the function.
Yeah, okay, y equals 3. So for part A here, we can just plug that in. 4 minus x squared equals 3. So x squared equals 1. So that means x is plus or minus 1. Okay? Now notice it asks for the coordinates of A and B, so we should give both points. So A is the point -1, 3, and B is the point 1, 3. Okay? So now if we want to find the actual volume of revolution, part B, we'll use the formula that we just found, pi times the integral from where to where? From -1 to 1 of the upper function. Which one is the upper function here?
Y equals Q3.
4 minus x squared.
The 4 minus x squared. This parabola is on top, okay? So this is our upper. Okay? That's our upper. So I need to do 4 minus x squared squared minus
Y minus 3 squared.
the 3. Okay, so 3 squared. Now, how do we get the integral of this? What are we going to have to do? We're going to have to FOIL it out, okay? So, pi times the integral from -1 to 1. If we FOIL this out, it's going to be an x to the 4th minus 8x squared plus 16 minus 9. 16 minus 9 will be 7, so that will be a plus 7 dx. So that's pi times x to the 5th over 5 minus 8x cubed over 3 plus 7x, evaluated from -1 to 1. Notice pulling out the pi like this really makes it easy because you don't have to mess with that until the very end. Okay? So if I have it at 1, it's going to be 1/5 minus 8/3 plus 7 minus, if I plug in a -1, it's going to be a minus 1/5, a plus 8/3, and a minus 7. So when I add all those together, I have pi times 2/5 minus 16/3 plus 14. If I add those, let's see, that's going to be, if I make it out of 15ths, I'll have 6/15 minus 80/15. That's a negative 52/15. Which is a negative 3 7/15 plus 14. So this is going to be 10 8/15 pi. Okay? So let's say this actually was some kind of a ring. If we were going to make this out of, gold or silver or whatever, now we can calculate how much material we're going to need and also then how much it's going to cost. Okay? Because we know the volume. All right? Any questions? Once you understand our original formula and you understand the area between two curves formula, really it's just a combination of the two. Okay?
So the day one stuff is just, it's just solid shapes. It's without the minus, it's just finding the integral of one thing.
Correct. Yeah, the day one that we did Thursday is just solid. Here we're cutting out an inside. We're hollowing it out.
The end, do we always have to be like 10 plus 8 over 15, or like can I just do like 158 over 15?
You can make it 158 over 15, that's fine.